This is example 1, and we'll use the convention of taking a cross-section at each point and calculating the moments to the left of that point in order to determine the bending moment. So we start off finding the bending moment at point A. So for illustration, MA, if we take the cross section through point A, I'll show in a dotted red line here, has nothing to the left of it. And if we wanted to be really specific and inclusive, we could say, well, we've got A itself, which is 7.2 kilonewtons. But of course, we're at this point, so the distance is actually 0. And so anything multiplied by 0 is 0 itself. So we have a bending moment of 0 at point A. And we would call this, the unit here, kilonewtons meter, because that is the units we use for moment, because it's a force multiplied by a length. Now, ordinarily speaking, we won't bother to include the force that's actually at the point, because its contribution to the moment will always be 0, because it's always at a distance of 0 from that point. So we've dealt with the moment at A. Let's look at C, a bit more interesting. This time we take a cross section at C, so this is a dotted line through here. So remember, this won't include this 5 kilonewton force because it's a distance of 0 away, but we now do have a force to the left, which is a distance away as well. So we look at MC, we've got to think about our direction here as well. Relative to C, the force acting up on the beam at A is going to contribute to a clockwise rotation, which means it's a positive value. So we've got 7.2 here, multiplied by the distance from C, which is 1 meter, and that gives us 7.2 kilonewton meters. And if we want to be explicit with the direction, we can put a little plus here to show that it's a positive reaction we're getting at the cross section at C in terms of our bending moment reaction. We can do the same again, this time with the bending moment at D. So if we do MD, B there, D. Again, if we take our cross section through B, and this time we have two forces to contend with. So we know we've got 7.2 at point A, but this time it's now 3 meters away, and we've got a force now acting in a counterclockwise direction relative to point D. So we're going to subtract the 5 kilonewton force at C, which is 2 meters away. We get 7.2 times 3 minus 5 times 2. When we put that into our calculator, we're left with a positive value of 11.6. And so a positive sign there to indicate that. Kilonewton meters. You'll sometimes see a little dot in between the kilonewton and the meters like this. It's actually fine either way. The dot, I think, is mainly to remind people it's not kilonewtons per meter, it's kilonewton meters, because the two quantities are being multiplied. Lastly, we can look at the bending moment point B. Take a cross section through that as well. And now we have all 3 of the forces to the left in play. So let's do that calculation. So we get MB is equal to 7.2, that upward force, and this now it's 5 meters away. And we'll have subtracting both other 2 forces because they'll be acting in a counterclockwise direction relative to point B. So we'll have 5 times 4, and we'll have 8 times 2. But actually, you put that into your calculator, what you'll see, and you'll come to expect this in these examples, is we're going to have a bending moment of 0 at point B. So it'll be 0 kilonewton meters. So 0 at either end of the beam in this particular example, and that is commonly the case. And we'll talk a bit more about why that is in the course. So that's how we solve this problem. So let's clear our screen just now and we'll move on to the next example. So here we have example 2 from the notes, and this is worth giving a bit more of our attention to because we are dealing with a uniformly distributed load, and we do things slightly differently, as we know from the previous section looking at reactive forces. So we'll take our time and we'll be careful with this, but the same principles we've been using so far still apply. So I'm not going to waste too much time re-explaining why MA equals 0. There's nothing to the left of A, so MA is 0 kilonewton meters. So let's move on to the interesting ones. MC, let's start with that next. So we've got C, this point here, and we've got two forces to consider. We've got the force that's been applied here at point A, and we've also got the contribution of the uniformly distributed load here. So that is a force in itself, and we have to consider it. So I'm just going to remove these two circles just now. So we know the effect that the 15 kilonewton force has relative to C. It's going to act to turn in a clockwise direction, so it's going to be positive. We've got 15, and it's 1.5 meters away, so we multiply that by 1.5. But now we need to consider the effect of the uniformly distributed load here. I'm just going to say UDL for short. We're considering over a 1.5 meter section of the beam, and if it's 5 kilonewtons per meter, what we're going to have here is 1.5 for the number of meters times 5 is going to give us a 7.5 kilonewton force to consider. And you remember from the previous section, when we have a UDL and we want to use the force it contributes in our calculations, we apply it in the middle of the section it applies to. So we're going to get a 7.5 kilonewton force applied halfway between A and C. So that's 7.5 kilonewtons. And halfway between 1.5 meters is 0.75 meters, 75 centimeters. So what we're actually going to have here is this part here. So this 1.5 times 5 that we've taken to get the force that's been applied. So we'll write it in full, because that's what we do in the notes. You might want to wonder what's going on there. So we've got 5 kilonewtons per meter times the 1.5 section of beam to get the total force applied, but it's being applied at a point halfway along. So this is multiplied by 0.75. So when you first see that in the notes, when you see the three numbers multiplied together, where are they coming from? The first part here is working out how much load from the UDL has been applied to the left of C, and this other bit here, the 0.75, that's the distance. That's this little line. Just draw it in here. That's a distance. I should actually put it between the midpoint and C, but it's the halfway point between A and C. And so when we put those into our calculator, what we're left with is a positive value. We can write it out first of all, 22.5 minus 5.63, which leaves us a positive value of 16.9 kilonewton meters. So that's how we deal with the UDL when we're considering a problem like this. So now we've got MC sorted, let's have a look at MB. Oh, I did that again, MD is what I want to look at. So we'll put our cross sections through here and then consider everything we need to consider. As before, the force at A, the 15 kilonewton force, is still acting clockwise relative to D, so it's 15 multiplied, and now A is a distance of 1.5 plus 2, 3.5 meters away from D, so this distance along here, 3.5 meters. Multiply that by 3.5. And again, we've got the UDL to deal with. Now this time the UDL is applying to this full 3.5 meter length. So it's going to be applied halfway along, which is a distance of 1.75 meters, that's half of 3.5, 1.75 meters away from point D, and it's going to be 3.5 times 5, that will be the size of the force. So the size of the force will be 3.5 times 5. And I believe that's 17.5 kilonewtons. I should have worked out beforehand, but it all comes out in the wash when we do our calculation. So we've got that force applied halfway along. So again, this is acting counterclockwise, so we're subtracting it. And what we're saying is it's a force of 5 for the UDL times 3.5, the length it's applied over, and we're multiplying it by the point we are experiencing it at, which is halfway between A and D, and we worked that out as 1.75 meters. I put that in. And once we put that into our calculator, it's going to come out as plus 21.9 kilonewton meters. So a positive bending reaction at point D as well. And lastly, we're left with the bending reaction at B. So I'll just clear this off the diagram again. So B is the end of the beam. So we've got two things to consider again. We've got the force at A, which we know, and we'll have the force due to the UDL. Now the total beam length, if we add this all up, we can see is 6 meters. So half of 6 is 3. So we're going to have a force being applied here. That's 3 meters away from B. And 6 meters with a UDL of 5 kilonewtons per meter is going to be a total of 30 kilonewtons. That's the 5 times 6. The 30 kilonewtons of force being applied there. So we'll have two forces to contend with, our force at A and a force in the middle of the beam as well. And that the spoiler is going to be 0 in this case, but we'll work it out anyway to show why. So we have 15, and now it's 6 meters because the distance between A and B is the full length. And we're going to subtract 30, but of course it's a half the way point. And you can probably see quickly that 15 times 6 and 30 times 3 are going to be the same, and of course they are. It leaves us with 0 kilonewton meters. And that is example 2.